Alright, so it's another Physics Friday. Looks like some people had difficulty making it in today with the snow. And so last time we talked about dark matter, someone had asked what's the deal with dark matter, and so we certainly can't talk about dark matter without talking about dark energy, with the reason that the biggest piece of this pie is dark energy. It also came to mind that when I was talking about this little sliver here, this is the stuff that we know. This is baryonic matter, atoms, things like that. There may be people that don't even know what's inside here. So a good question might be, what are quarks, or what's the standard model of particle physics, or something like that. That could be another good question where we can talk about this little sliver. Right? There's lots of exciting stuff on this very simple diagram. So today we're going to talk about this extra 71.4%. Last time we said that this dark matter was probably WIMPs. So these were weakly interacting massive particles, things that we know don't interact with the electromagnetic spectrum, but may interact with the weak quarks. Okay, so what's the deal with dark energy? Why do we know that it's there, or why do we posit that it's there? And the reason is basically because the universe is accelerating, it's expanding. There's lots of excitement last year. There's BICEP results that are maybe still a little bit controversial. It's basically, purport to prove the expansion of the universe, and there's lots of different ways that we understand that the universe is expanding. And so what's the deal with the dark energy? Well, it makes up that pie chart basically through the connection of the famous E equals mc squared equation, that if there's some energy that's driving the expansion of the universe, c here is the speed of light, then we can basically associate that dark energy, the thing driving the expansion, with the mass. Okay? And so the reason why dark energy makes up, so dark energy, the dark energy density, we'll learn about that in a little while, is very small, but it's basically homogeneously distributed everywhere through the universe. And so that's why it makes up such a huge piece of that pie, that it's basically everywhere. We know that mass that we can see, things like stars and planets and whatnot, gas clouds are clumpy, right? You look at the sky and you see clumps of stuff, the Milky Way, whatever. But dark energy is kind of universally distributed everywhere. All right, so how do we know that the universe is expanding? People have probably seen some of this stuff before, and we'll actually learn about Doppler shift later on in this class. But probably the most convincing thing about the universe expanding is that as we look at stars and galaxies that are farther and farther away from us, they seem to be moving faster and faster away from us. Right? So things that are close are moving at some speed, things that are farther are moving at another speed, and that's basically what this plot is telling us, that as we move farther, so megaparsecs is the unit of distance, so the things that are further apart from us are moving faster and faster away from us. And we understand that in terms of something called the Hubble Constant, which is a measure essentially of the rate of expansion of the universe, and the Hubble Constant can change over time, because R is some measure of the size of the observable universe. And so how do we know that things are moving away from us? Well, we do it with something known as redshift, which is basically we look at chemical processes that we understand here on Earth that we can see in the laboratory, and then we look way out at some star or some cloud of gas that's way far away from us, and we see that absorption line, so this is a visible spectrum, we'd expect to see some line here, but instead we see it here, let's say. And so this is basically telling us that we're getting a Doppler shift, everything's shifting to the red, which is why these lines are going up, and so this tells us that things are moving away from us. Right? Just as when you hear a police siren or an ambulance that's driving away from you, you hear the shift in the frequency of the sound. It's the same thing with light, right? It's a wave, and so we see this, observe this shift. So this is basically what tells us that things are moving away from us. But then you might ask, well, how do we know actually how far away from us stuff is? And so that's actually rather exciting. So we use something called standard candles, and in particular type 1a supernova. So this is a type of supernova that's very well understood. They basically always have the same peak luminescence. So if you look at these type of supernovas, so this is essentially what happens is you have a binary system, and that binary system kind of spirals in on itself. The larger star wins, and then there's an explosion, supernova. And so we think that we understand this type of process extremely well. And so whenever we look at these in different places, they all have this first peak, this huge luminescence. So this is the flux over this is different wavelengths of light right here. And so this peak right here is basically uniform. So whenever we see a curve that looks like this, we say, aha, we've discovered one of these type 1a supernova. And so if we know exactly this luminant flux, this would be the actual magnitude. So we observe on Earth some apparent magnitude, how bright this event is. We know because of the physics of what's going on here what the absolute magnitude is. And through this equation, because of essentially the inverse square law of how the energy is being distributed as it comes to us, we can get a feeling for the distance, and this is the distance in kiloparsecs. And so basically understanding the mechanism of these type 1a supernova and then finding them in the sky led these guys to get a Nobel Prize in 2011. And so now whenever we see one of these, right, we say, okay, I see this, and because of understanding the physics, I know exactly how far away it is, and I can look at the redshift, and then I can say, okay, it's moving away at this speed. And so through that, we can correlate the things further away from us that are moving faster, which is telling us that the universe is expanding. And that expansion is driven by some energy density of the universe, which is dark energy. So there's other ways we know that the universe is expanding. So people have probably seen this picture before, right? This is the cosmic microwave background. So these are tiny, tiny, tiny little temperature fluctuations that exist everywhere in the observable universe. This was taken in the so-called Planck map. So basically the temperature of the universe in Kelvin is incredibly uniform, plus or minus some tiny little variations, which is what you see here. So these variations are on the level of microkelvin, right? 300 microkelvin, that's 10 to the minus 3. So these are really, really, really small. And so the point is, okay, this means that the observable universe is incredibly uniform, right? But there's a big problem with that uniformity, because we know essentially how old we think the universe is, and we know that information can only travel at a fixed speed, the speed of light. So then how can everything get so uniform if there hasn't even been enough time since the age of the universe for information from, let's say, the right side to transmit to the left side? Right? So there just hasn't been enough time for it to be so uniform. So think about, you drop a little bit of dye into a pot of water, right? And you stir it around, and eventually it'll all get mixed around. Well, if you don't wait enough time, then it's not going to look very uniform. So basically this means that the universe must have been much smaller at some previous time. Then information could be transmitted around so it could look so homogeneous, and now it's expanding. Right? So this is pretty concrete evidence that the universe is in fact expanding. Okay, so then this leads to the natural question, well, what is going to be the fate of our universe? And there's basically 3 different possible fates based on how much dark energy there is. And so these fates have kind of funny names: the Big Rip, the Big Crunch. So basically, if there's too much energy, there's too much dark energy, then the universe is just going to keep expanding, and then eventually everything will be so far apart from each other that it's just going to, you won't be able, light from the sun will never be able to get to the Earth. Basically, everything will be too far apart. So that would be the rip. There's the Big Crunch, which basically means the energy isn't enough, so eventually gravity will overtake the expansion of the universe, and everything will come back down and we'll all be squeezed, and maybe there'll be another Big Bang after that. And actually what seems to be the case from the observable universe is we have these rapid periods of acceleration after the Big Bang. This is where we are right now. It seems that there's just enough dark energy to keep everything kind of expanding that will eventually come to a finite size. So it seems like we're in this balance case. And this is related to the fact that we have a constant cosmological constant. That cosmological constant is a measure of the dark energy. All right, so there's a very good model for this. It's called the lambda CDM model. So where does lambda come from? Lambda is usually the symbol, this capital lambda. Upside down triangle is the symbol that we usually give to the cosmological constant, which is a measure of the amount of dark energy. And so basically this is some background energy density that imbibes all space, and it's really, really small, 1.67 times 10 to the minus 27 kilograms per meter cubed. So that means it's about 6 kilograms of dark energy converting to mass in our solar system. So again, that's not very much, right, 6 kilograms, but it's everywhere. Right? It's everywhere in all of space throughout the universe, and so that's why it makes up such a huge amount of that pie chart. Okay, so then the question is, well, where is it coming from? What's the origin? This essentially space itself is imbibed with this energy. And the easiest way to understand that within these models is that once you have vacuum, particles are basically coming into existence and winking out of existence whenever you have some space for them to do that, right? This is basically particle fluctuations, and those fluctuations imbibe the vacuum with some energy, and that can be described with Einstein's field equations, where this right here is the cosmological constant that measures this background energy density of the universe. All right, so what's driving the expansion now? Well, we can basically appeal to very simple laws of thermodynamics. So basically, this lambda CDM model tells us that the universe has a negative pressure. It's expanding, right? That's the definition of negative pressure. And we can understand this just from the first law of thermodynamics. So some energy change is related to heat and work, right? If we want to expand something, we have to do work. So the work done is basically given by the integral of PdV. Chemists should be very familiar with these expressions. But when space expands a small amount of dV, the total energy actually increases because now there's more space for particles to wink in and out of existence in, right? So there's more space, which means there's more energy. So somehow the energy is actually increased by expansion, and that's the opposite of what we normally think. So that means that this du, which is just minus PdV, so a small change in the energy density is related to PdV, just from this expression here for the work. And so that tells us that there has to be a negative pressure, right? So the only way that this expression can be positive, which is what's driving the expansion of the universe, is if the pressure is actually negative. So there's an implied negative pressure everywhere in our universe that's driving this expansion. So the density is so low, what did I say, 10 to the minus 27 kilograms per meter cubed, right? This is really, really, really small, so it's probably unlikely that we'll be able to measure this in a lab somewhere on Earth, but we might be able to measure it in larger structures in the universe, and there's basically two huge, large-scale scientific efforts to search for dark energy. One is basically really trying to understand this relationship of the expanding universe better, so that's looking for type 1a supernova. And another one is something called baryon acoustic oscillation. So this basically says if the universe expanded very rapidly, this rapid expansion could imprint itself on the matter density, or there could be matter density waves showing up. And so it's kind of hard to see this, but basically there's some patterns here that are related to the where the visible mass is in the universe, and they basically would have been created right at the start of the early universe. And so these are ongoing. There's lots of exciting stuff. As I said, BICEP results just came out last year with pretty good evidence for expansion, although as I said, there's some controversy there. But again, this is an ongoing thing, trying to figure out really what's the origin of this 74%. Is it the perfect amount such that the universe is not going to crunch back in on itself or keep expanding to nothingness? All right, so any questions? Yeah?
What exactly does negative pressure look like?
Yeah, so it essentially just means that if I expand, so normally I need to do, I have some gas that expands, right? And so then the energy gets smaller when I do that. But for our case, when we expand a little bit of our space-time, if you like, because of this constant cosmological constant, the total energy is increasing. And so that just means that there has to be a negative pressure, right? So it just comes out of the first law of thermodynamics. Yep?
It doesn't really make sense. So if space is being created, then that just makes no sense. Space is a thing. If you're making more space here, there has to be something that you're taking away from something else.
Yeah, so we imagine that if the Big Bang is really what happened, which seems like that's the case, then our universe started out being essentially of no volume, and now it's expanding. So there's basically more space-time is being created. So we live in some expanding universe, so I think it's difficult for us to imagine just the pure scale of that, because this is our universe and it's not changing in size, right? But the entire observable universe appears to be expanding. It's really changing in size. There's more stuff, more space-time that's constantly being created as we expand. So think about it like someone's just blowing up a balloon. So there's more space being created inside that balloon, right? And so that space, because of the constant cosmological constant, is imbibed with some energy, and that's related to essentially models of particle physics, where particles are winking in and out of existence. But I've kind of swept something under the rug. So if you take that at face value, that this is the origin for the cosmological constant, so you could then calculate it based on certain models, standard model, for example, and you get a number that's 100 times too big. So we're definitely missing something. We can't calculate these numbers. What lambda is basically measured. We can't calculate the value of lambda. That would be awesome if we could. But we know what its size from essentially the Einstein field equations and what we need to see or create the expansion that we observe. Yep.
Kind of like a dumb follow-up question, but so we really dumb question. So our universe and the whole galaxy thing, where are we on a hierarchy? Is the universe everything?
Yeah, so the universe is everything. So there's galaxies at large scale, clusters of galaxies, and we're just, we're in a solar system in one of the spiral arms of our tiny little galaxy. So everything is expanding, right? So the distances between me and you is basically expanding. It's just expanding very slowly. It's expanding on time scales of the order of billions of years.
So it's just like blank space.
Yeah. Question up there?
Yeah. So on that slide where you showed the face of the universe,
Yeah.
you said that it looks looks like you were about like halfway toward everything being
Yeah, right, so if, of course this is a very schematic picture, but for some models, this is exactly what would happen. So if we waited, so this is 14, 15 billion years or whatever, so if we wait double that time, then based on some more extreme models where there basically wasn't enough dark energy, then everything would, think about it, everything gets kind of slowing down, then there's so much mass in the universe, gravity starts pulling everything back in, and once that starts happening, everything's just going to come and crush down to a point. And then presumably there'd be another singularity, and we'd start again. So maybe this is the 17th, universe that there's been, or maybe it's the first, or I don't know. It's if that's the case, this would be some oscillating cycle.
So like it's that red graph or red line?
Yeah, this is where we think we are. Yeah.
So what is that like? What are the implications of that being true? The universe doesn't fly apart.
Yeah, so this is the best case scenario for us. We just kind of, everything's in equilibrium, and we kind of reach a constant size where the expansion will eventually slow down, but everything will be balanced by, the kind of negative pressure, which is pulling us outward, pushing us outward, and then gravity, which is pulling us inward. Yeah. So this is the best case scenario for our descendants in 18 billion years or so.
So I mean, this should be concerned about the big bunch.
Potentially, yes. Other questions? Yeah?
Going back to the slide we were on,
This one, or which one?
just wondering,
This one.
yeah, what's the picture of the
Where is it right now? Or what are we seeing here?
Yeah, what are you seeing?
Yeah, so this is just basically a specialized set of telescopes that are set up just to look for these special type of type 1a supernovas. And so the more we have, then the more data points we can put on that graph, and we can really understand the Hubble constant, because knowing about how fast the universe is expanding, which we can do by studying these type 1a supernova, these standard candles, gives us very precise measurements of that Hubble constant, and that will tell us basically how fast the universe is expanding. Yeah, so these are kind of different approaches. This one is really about measuring how big lambda is in a very precise way, and this is really about understanding, are we really expanding? Other questions?